So let's have a look at one example where we will see this chain rule with two independent variables in action. All right, so it's on the next page, page 3. So we're given a function z, that's the dependent variable, and that depends on two variables, x and y. But at the same time, both x and y depend on s and t. All right, first of all, tree diagram. Why not? Z, which depends on x and y, and at the same time x and y depend on s and t. All right, so they're asking us for an expression. First of all, the derivative, the partial derivative of z with respect s. However, looking at this crazy function, well, there's a couple of ways to go from z all the way to s. That is, there's two branches. So that means we need to go, let me use red for this. So let me use from z to x and then from z to s. That is, in this case, they are all going to be partials. And then dx and then dx ds, plus the other branch that also takes us to the variable from z all the way to s. That is going from z to y and from y to s. Okay? That is partial of z with respect to y times partial of y with respect another s. So here we're looking for the change in with respect the change of s with respect x. However, going through two contributions, the x contribution and the y contribution. Well, let's find the required partial derivatives. That is, the derivative of the function z, which depends on x and y. We will differentiate this with respect x and with respect y in a second. So this one right here, that's going to be the derivative with respect x, well, that's itself times e to the x itself times times sine y, times the partial of x with respect s. That is, the partial derivative of that basic function here, x with respect s. Well, the derivative of s, there is just one. That one times the t squared right here, that's just going to be t squared. I would put parentheses around the y right here just to avoid any mistakes with putting that t squared as the angle of the sine function. So carefully there. All right, so plus the partial derivative of z with respect y. Well, in this case, the derivative of sine, which is cosine times the multiple constant e to the x, that's e to the x cosine y, times the derivative of the y expression, this time with respect also s. So here the derivative of s cubed is 3s squared times the t, that is 3s squared t. Okay? And again, we will end up with an expression that involves x's, y's, and t's, and a bunch of variables, also s's. So here we need to get rid of the middle, or rather the intermediate variables. We need to write all x's and y's, the intermediate variables, in terms of their equivalent in terms of s and t. So every instance of x, I will replace with st squared, e to the s t squared, sine y, which is s cubed t times t squared plus e to the x. What is that? E to the x, which is again st squared. I'm going to run out of space here. So this will be times sine of y, which is s cubed t, times 3s squared t. And to be honest, guys, there is really not that much to do other than putting the coefficient t squared e to the st squared sine s cubed t plus 3s squared t e to the st squared sine s cubed t. So now this is why we have a partial derivative this time, because our result, our final result, no longer depends on one single variable t like in the previous example. This time it depends on two variables, s and t, or potentially three, st and r maybe, or st and u, w, r, I don't know, 5 independent variables, 7, doesn't matter. Okay, so now the thing is, these are going to be partial derivatives now. All right, for letter B, actually, how about you guys try letter B? The cosine right here, that should be a cosine here, right? Yep. Okay. Okay, to help you out a little bit with part B, now consider all the branches, all the possibilities to go from z to t this time. That is, z to x, x to t, z to y, y to t. All right? All right, looks like almost all of you are almost there. Okay, let's get started with the expression first. So, to go from z to t, we need to go from z through x and then from x to s. That is the partial of z with respect x and then the partial of x with respect t, plus from the contribution from the other branch, z through y and then y through t. That is partial of z with respect to y, partial of y with respect to t. And let's just find the partial derivatives in a similar way we did in part A. Okay, so partial of z with respect x. Again, we're going to get the exact same thing, I think. So e to the x sine y. It's the x with respect t this time. That'll be 2 st plus the partial derivative with z with respect to y. It's the same. E to the x cosine y times the partial derivative of y with respect to t. But the derivative with respect to t is just 1 times, what is that? S cubed. That's just s cubed. Okay, so we're done with the calculus actually. Let's just back substitute every instance of x with the expression that is st squared, and every instance of y with the expression s cubed t. That way we get a result in terms of s's and t's. That is in terms of the independent variables. So that is going to be, okay, so e to the s, was that st squared? Sine of s cubed y, or rather t, plus e to the st squared cosine s cubed y times s cubed. And to be honest, there's not much to do other than, oh, I forgot the 2st here, times 2st. Let me just write those 2st and the s cubed in the front of the exponential. 2st e to the st squared sine s cubed t plus s cubed e to the st squared cosine s cubed y. All right?
Shouldn't the y be?
Which one?
Should the y be changed to s cubed t?
S cubed t where? Oh, yeah, s cubed t. Yeah, t. T, I don't know why I was sticking with y. Thank you. So that is our result in terms of s and t's. And of course, again, there's no limit as to how many independent variables, as to how many intermediate variables, as long as you have enough letters in the alphabet. If not, go through the Greek alphabet, maybe any other symbolic system. I mean, there's no, or make up your own symbols to keep coming up with many other variables. And well, if you wonder how does that work in the real world, of course, I mean, having too many variables beyond two variables, which describes surfaces in space, more variables can be thought of parameters. For instance, if you're working in the industry, all you do is work on Excel and manage all the variables in Excel. So there's really no 75-dimensional object. It's just all the parameters, all the elements that are required, for instance, to manufacture a product. So it requires those 75 parts, for instance, and well, those are variables, So, um, okay, so enough of chain rule. Let's go about implicit differentiation. Okay, so let's recall how we do implicit differentiation for with functions of two variables, the way we did it in calculus 1. Okay, so number 1. Let's find dy dx given x squared plus 3xy minus 5y squared equals 10. So why do we go about implicit differentiation? Well, that's because we have an implicit function. Well, I mean, but what's an implicit function? It's a function that cannot be written as an explicit function of the dependent variable y. That's because if you try to solve for that y, notice you have a y squared, you would have to use the square root property. That would give you two results, a positive and a negative. So, and also, well, that's really not a function because, well, for every single value of x, you would have two different values of y. So can you be in two different places at the same time? Again, well, that's not a function. Okay. Let's find the derivative of this implicit function, okay? So, well, to differentiate using the implicit function, we use the exact same rules. Okay, the derivative of x squared, that's 2x, plus 3 times, okay, I'm going to factor out the 3 times, I'm going to save that for later, and I'm going to focus on the xy, that's going to require a product rule to be differentiated, okay? So the derivative of x times y, that is 1 times y, plus the derivative of the second factor, which is y times the first factor. But again, when it came to implicit differentiation, what do we do when we differentiate the variable y? Multiply by dy dx, okay? So multiply by dy dx. So that is dy dx, or y prime, either way, times, in this case, what's that? X, all right? And then the derivative of negative 5y squared, isn't that negative 10? Negative 10y. But because we're differentiating a y, multiply by dy dx. On the right-hand side, dy dx, for 10, that equals to 0. The derivative of a constant is 0. Let's clean up the mess on the left-hand side and get the derivative. So that is 2x plus 3 times 1y, which is 3y, plus 3x dy dx, minus 10y dy dx. And let that be equal to 0. Alright. So the idea of solving or of using implicit differentiation is to treat this problem now like an equation, where the unknown variable is going to be the symbol dy dx. I know dy dx at this point in time, you know, it's a quotient between two quantities that describes the rate of change between the dependent variable and the independent variable. But back then, when you first learned about differentiation, it was just a symbol. And this time we're going to go back to those times. So that is 3x dy dx minus 10y dy dx. So we want to isolate all the terms containing the dy dx, and all terms that do not have the dy dx, move them to the right-hand side. Okay, that is negative 2x minus 3y. And well, why do we do this? To make that dy dx a common factor, factor it out, and divide out the rest of the factors. That is dy dx times 3x minus 10y equals negative 2x minus 3y. Okay? So, that equals, okay, solving for dy dx, that is negative 2x minus 3y divided by 3x minus 10y. And just to recall, why do we multiply by dy dx every time we differentiate a y variable when we are doing this implicit differentiation? Well, let me give you an easier example so you can visualize it in an easier way. Okay, x squared plus y squared equals to 5. So let's find the slope at every single point for a circle radius 5. Well, radius square root of 5, I mean. So, I mean, to differentiate the y, so again, using the general power rule, to y dy dx, that's because we're essentially doing a chain rule, right? Y is depending on x. If we thought of the same for the x variable, that is 2x, well, x dx dx, I mean, x is depending on itself, but what is dx over dx? Isn't that just equal to 1? Which results into 2x plus 2y dy dx equals 0. So that's why we always multiply by dy dx when differentiating the dependent variable and not the independent variable, right? So in a way, there is a chain rule on the behind the scenes when we are differentiating dx, but it's called dx, but that's meaningless. That's just 1, isn't it? I mean, so. Okay. So that's why. How do we go about implicit differentiation with functions of multiple variables? Sounds like it's going to be a nightmare, right? But trust me, it's not. Yes, actually, that problem we just did, it's a nightmare compared with what we're going to do in Calc 3. You'll see. So, and like I mentioned before, you would wish you knew this in Calculus 1. But first of all, of course, I'm going to do the derivation of the idea. I can give you just a formula, but I mean, let's make it spicier, you know. Let's have that flavor and see where is this coming from. So in the end, okay, we have a function z that depends on x and y, all right? And then at the same time, x and y depend on a third variable t, or third party variable t. That is the independent variable, the, what is it called? The intermediate variables x and y, and then the dependent variable z. By the chain rule, dz dt, is that equal to the partial of z with respect x, whoops, times the derivative with dx dt, plus the partial derivative of z with respect to y times dy dt. Where did I get this from? Again, tree diagram. We have a function z that depends on x and y, and at the same time x and y both depend on d, right? Again, that's the first case for the chain rule. The first one we discussed during lecture. Okay, let's make a couple of changes here. So let's So here is the thing. I'm gonna come up with another equation, and it seems like I'm gonna come out of an equation like in the middle, like from out of nowhere. Okay. So let's define that function z that is given as some big f of y. Okay, and let that be equal to 0. Why? Okay. So. This means, so z equals to, well, let me use little f, not big F. Little f is fine. Or no, hold on. Okay, so again, we have this, right? Z equals to the function f of x, y, right? The two notations, the dependent variable explicit notation, or the function notation to denote that this function is depending on x and y. So this is what I'm going to do. I'm going to move f to the left-hand side. Now I'm going to treat it like an equation, not just a symbolic idea to denote a function. No, it's an equation today. And let that be equal to 0. Now, because I'm coming up with a new function big F equal to 0, 0 equals to big F, then this new equation here is big F of x, y, which is equal to 0. All right? Okay, the next step for the derivation is to use that chain rule expression, that chain rule formula, if you will, but I'm going to replace the x's. Oh, hold on. This is supposed to. Oh no, we're good. We're good. I'm going to replace all the t's with x's. Why? Because I want to find the rate of change or the derivative of f with respect to x. All right. So no longer with respect t. So this will be the following, and I'm going to replace this z with a big F. Okay? So, changing the variables rather, that is partial of f with respect x times dx plus partial of f with respect y dy dx. So all I did is I replaced the t's with x's, okay? Nothing really interesting. But well, here's where it comes, where it goes. Interesting. Number one. What is dx again? 1, right? So that's why I discussed the Calc 1 version of this. But also, I'm going to set this equal to 0. Why? Just because? No. That's because this f, this big F that I define as z minus little f, it is equal to 0, isn't it? So if I find the derivative of big F, isn't that little f? And what's the derivative of 0? Isn't that it still equal to 0? So that's why this is still equal to 0. And now I'm going to work with an equation. I'm going to work with this equation here. That is the partial of big F with respect x times 1 plus the partial of f with respect y times dy dx equals 0. And I'm going to treat this like an equation because what do we want? We want dy dx to come up with an expression or a formula to do implicit differentiation. So number one, I'm going to move this df dx to the right hand side with the opposite sign. That is df dy times dy dx equals to negative partial of f with respect x. And while dividing both sides by df dy to get the dy dx, check this out. That's going to be negative partial of f with respect x divided by partial of f with respect y. And that is the end of the proof. That is the end of the derivation. Actually, this is the formula you have in the definition box below. All right? So what do we have? An equation z equals some big F equals to 0 that will define a function implicitly. Okay. So we need to get used to these implicit functions because we're going to need this for later when we do a lot of the linear approximations. What else? Differentials and max and min. We'll do a lot of this. Okay, we'll use a lot of this. So y implicitly as a differentiable function of x. Well, so if we define this as an equation, we can find the derivative by implicit differentiation by simply finding the partial of the new function with respect x over the partial with respect y with the opposite in sign. You will see how easy is this. Okay, let's have a look at example number 5, the last example in our notes. So given big F. Big F of x, y equals to x squared plus 3y minus 5y squared minus 10. So it's the same exercise we did in the previous page, except that what did we have? X squared plus 3xy minus 5y squared equals to 10. So we moved the 10 to the right hand side. So let me make it a minus and set it equal to 0. So now, because this defines a new implicit function, we can set that big function we just created equal to big F, which is this. All right. Okay. What's the partial of f with respect x? That is 2x plus 3y. And what's the partial of f with respect y? That is 0, 3x minus 10y. 0. And well, what's the implicit differentiation dy dx? That is negative f with respect x over f with respect y. What is this? 2x plus 3y over 3x minus 10y. Don't forget the negative. Isn't that the same result as we did before? rather than spending 5 to 10 minutes doing the implicit differentiation in a blink of an eye, right? Didn't you wish you knew this in Calc 1? Yeah, but I mean, not that you guys were not able to compute these partial derivatives, it's just that concept-wise, what is a partial derivative? It would be too early for you to look at differentiation with more than one variable when you were barely grasping the single variable differentiation, right? That would have been overwhelming. So now that you have all that training, just use those tools to magic, right? All right, that wraps up the section.